Now, here's something really powerful that vectors lets us do. It's possible to define a fairly simple equation that defines a plane in 3 dimensions. Let's start with what a plane is. A plane is just a big flat surface in 3D space. Anything that's in some sense flat. I've got to be more precise than that though. How do I define this? Well, if I find a single point that I know is on my plane, then I can get to every other point on my plane, could be anywhere, with a vector from P1 to my point P. So the vector from P1 to P goes from P1 to every other point on that plane. But every vector within that plane is perpendicular to a normal vector from that plane. So I can define this plane by a single point and a normal vector. And as your textbook notes just a little bit below, you don't have to draw these two vectors at the same point. But it's easier to see if we do. Just go back to where it was. It may take you a little while to get your head around this. I can define any plane in 3D space by having a point on the plane and a vector that's normal to that plane. And how do I go about defining it? I say any vector from P1 to P, which is P minus P1, any vector from P1 to P, dot product with the normal vector must be 0. Because then whatever vector I've created in that plane is at right angles to my normal. Any two vectors that are at right angles will have a dot product of 0. If you need to, go back and listen to that explanation again. So, if I have a point P1 on my plane, x1, y1, z1, and some general point P anywhere on my plane, so x, y, z is any point on my plane, the vector in the plane is from P1 to my arbitrary general point P. So the vector from P1 to P is P minus P1. How do I express that using x, y and z's? P minus P1 is x minus x1i, y minus y1j, and z minus z1k. Now what I have to do is get this and get the dot product with my normal vector to be 0. Well, the dot product with the normal vector, here's my normal vector, ABC, and I'm getting the dot product of that with the P minus P1 that I just worked out. Well, the dot product of this is fairly easy to work out. It's A, x minus x1, and B, y minus y1, and C, z minus z1. So this is an equation that defines a plane in 3 dimensions. All I need to define the plane is my normal vector A, B, C, and some point P1 that I know is on the plane, x1, y1, z1. Just to reiterate, you don't have to actually draw these from the same point. They're vectors. They just give us directions.